Question 1 follows directly from our lesson of impulse momentum theorem. The question reads as follows. A 900-gram stainless steel ball is thrown vertically downwards at 15 meters per second. The ball collides with a hard surface and rebounds with the same speed. During the collision, the ball is in contact with the surface for 5 milliseconds. And they've given us a diagram here to assist us to have a mental picture of the problem. The first thing that we're going to do in this problem is that we will interpret this problem before we try to answer the questions. And this diagram will play a significant role in helping us to interpret the problem. That's the reason they usually will give us diagrams in our exam papers. The first thing that I'm going to do here is that I'm going to choose direction because I've realized that this object actually has directions. It moves downwards. So I'll choose anything that goes to the right as positive and anything that goes upward as positive. This would mean that anything that goes down should be negative. Now, the ball is actually going down with a velocity of 15 meters per second, vertically downwards, as we can see here. This means I'm going to have a negative 15 meters per second since it is going in the negative direction. And the other thing that we note here is that this ball has a mass of 900 grams. The ball at some point here at the bottom, they say that it collides with the hard surface and then rebounds, meaning it goes back upwards with the same speed. Now remember that speed is a scalar quantity, so this is to say our final magnitude of the velocity is 15 here meters per second. But you have to keep in mind that we want to write this as a vector, as a velocity instead, not as speed. So that means we'll consider the direction to say it is now going upwards, it's going to the positive direction, and this here would be a positive 15 meters per second to say it's going upwards. Now they say during the collision, at this point here, when it collides with the surface, the ball is in contact, it stays in contact. It stays in contact with the surface for a very short time, really, which is given by 5 milliseconds. Remember, milli is a metric multiplier that we write as m. Now, at this stage, I've completely interpreted my problem. I know what's going on here. I can further go and write down my given information so that I also convert the mass and convert the time to be in SI units, so everything to put it down properly. The mass is given here by 900 gram, and we know that 1 kg is the same as 1000 kilogram. The technique that I shared with you earlier on is that you divide here by 1000 gram and you put the 1 kilogram as the numerator. You do this because you actually want the gram and the gram to cancel, so that now you'll be left with 0.9 kilogram and the kilogram would come here. Now what I've done here is that I actually took the 1000 and put it in the denominator and took the 1 kg and put it in the numerator, because I want the gram and the gram to cancel so that I'm left only with the desired SI unit. Now the other thing that I'm going to note down is my initial velocity. To say I have an initial velocity of negative 15 meters per second. Then I have the same magnitude of the velocity, which is 15 meters per second, but now it's positive because it goes upwards as a velocity. Remember, we are reporting this as a velocity. Then we have the time that is given by 2 milliseconds, and we know that a milli is a metric multiplier. That means 10 to the power negative 3. So I'm going to write this as 2 times 10 to the power negative 3 seconds. So I'll just literally take this milli and replace it with its metric multiplier. That's how you convert metric multipliers. Now, the next thing that I'm going to do is to classify this problem, the C. The classify part means that I ask myself, which part of physics does this question fall under? I see this problem as the one that requires the concept of impulse and changing momentum. The reason why I'm saying that is because when the ball hits the surface, it collides with the surface will actually exert a force that goes vertically upwards. Hence, this ball actually changes direction and go upwards because the surface exerts a force. And this force will be exerted over a time of 5 milliseconds. And it's a time varying force, the force that is exerted there, which will average it to a net force. We spoke about this in our 2 previous lessons. Now, from this information, I can see that I have time, I have a force, I could produce impulse. I also have the velocity and the mass, and also final velocity and the mass. So that means I can talk about changing momentum, because the momentum would change here, V final and minus V initial. Now, this for me is a problem that requires impulse momentum theorem, the understanding of impulse and momentum. Then now I have fully understood the problem by interpreting and classifying it. It means I'm ready to then answer the problem. I'll go to the next step, which is A, answering the problem. Now, this step, I literally go to my questions and answer them. The first question says, state the impulse momentum theorem in words. So remember, we can express this theorem in terms of an equation. So here I'm going to answer it in words as requested. The theorem says that the impulse of the force acting on an object is equal to the change in momentum. After I'm done writing my question, I'll take a further step to actually navigate my problem. The N there will stand for navigation. Navigate means I look at my answer. I can see that the type of question I was asked here is a question that focuses on concepts. It requires me to define impulse momentum theorem. As opposed to a calculation problem, it's not a calculation problem. So with this type of a problem, you check if there's any errors, typing errors here, or other grammatic errors, and if your sentence also makes sense. So here we're saying the impulse of the force. Maybe I can say the impulse of a net force, because we know that it is the net force. Let me reduce my eraser. So I can say here the impulse of a net force, the impulse of a net force acting on an object is equal to the change in momentum. It looks good to me. This will always give you 2 marks. Easy peasy. Then now we will cycle back to answering the question. We go back to this part of answering the question because we have another question, the next question, which is 1.2. This question says to us, calculate, and then we have sub questions here. So we have 1.2.1 that says calculate the impulse applied to the ball, right? So when this ball is in contact with the surface here, there will be a force and a time, right? That will give us the impulse. There will be an impulse because there's an impact, a collision. They want us to calculate that impulse. You have to note that we don't have a force, so we can't just multiply a force and a time because we don't know what this force is. But we know from the impulse momentum theorem. Remember that we are requested to find impulse. We know from the impulse momentum theorem that impulse is equals to the change in momentum, right? So that now the change in momentum, we know that is defined as the mass final velocity minus the initial velocity. And now I can then substitute my mass of 0.9 and the final velocity is here a positive 15 and our initial velocity is minus 15, right? So here it means I need to use square brackets because I have a bracket inside there. So what are we saying here? We have the final velocity of positive 15 is this one here. Then we have this minus which is going to come here. Then we said our initial velocity is negative 15 because we chose down as negative. Now this would then continue to say we can use our calculator at this stage. So I'm just going to punch the whole thing in the calculator to say we have 0.9 15 minus 15 close bracket, and that gives me 27 Newton seconds. Now you have to note that my answer is positive. This means that my impulse is actually going upwards. Remember, impulse is a vector quantity. Again, because we have answered this question, we then need to navigate the question to see now if it makes sense and there's no mistakes in our question. This is a calculation question. So a calculation question, it has to be reported by a number and the SI unit, which we have done, and also direction because impulse is a vector quantity. And it makes sense that our impulse would actually be positive because remember that the force and the impulse are directly proportional, meaning they always point in the same direction. So it makes sense to say the impulse that is delivered to the ball should be upwards because, this ball experiences a force that goes upwards and hence it's going up, it rebounds. You can also report this answer such that you say this is 27 kilogram meters per second upwards. Is the same answer. Remember we said 1 Newton is the same as 1 kilogram meters per second. We will again go back to the A for answering the question because we have the next question 1.2.2 which says calculate the average force exerted on the ball by the surface. Remember the average force would be the net force. As we said that this ball here will experience a time varying force. There will be a number of forces that it experiences when it's in contact with the surface. And those forces, we average them, right? And hence we call it the net force, which is the average of those forces. So when we say the average force, we mean the net force. So we are looking for the net force. Net force. We discussed this in a lesson when where we were breaking down the definition of impulse. Now, at this stage, I will use the formula of impulse momentum theorem that says the net force times time, which is the impulse release. The same formula as this. I'm just writing impulse in terms of its definition. The net force times the force, to say this is equal to the change in momentum. But now we know, we can substitute now. We know that the time is actually 2 times 10 to the power negative 3. And our impulse, we really calculated that in the previous question to be 7 Newton seconds. At this stage, this question becomes very, very, very boring, because we have to then now divide by the 2 times 10 to the power negative 3, and this side also divide by 2 times 10 to the power negative 3. Now this and this would cancel, and I'm only going to be left with the net force, and I'll punch that in a calculator. So here I have the net force is equal to, now on my calculator I'll have the 27 divided by 2 times 10 to the power negative 3, and this would give me a force of 13,500 newtons. And again, this force is actually positive. That means it's going upwards. And now we can navigate this answer to see if it makes sense. Yes, I'm expecting my force to go upwards. In fact, we talked about that when we interpreted the question, to say the surface will push back on the ball when they collide. That's why it's going upward and rebounds. So the answer makes sense in terms of its direction. And I've written the SI unit and the number, and of course I was calculating the net force. The other thing maybe that I can entertain quickly is that this number is a very big number. I do expect to get such a big number for the force, because remember that from Newton's second law, we said that the net force is inversely proportional to the change in time. If you look at our time is extremely small, right? We have an extremely small time. It means we'll have a big force. So that answer makes sense to me. Now, after navigating this problem, we'll continue to go back to answer our question. But in fact, when you look at this here, they give us additional information. In other words, this information will require us to actually go back to the beginning and interpret the problem and then go to classification and answer again. So I'm going to read the second part of the question. They say to us that a slightly deflated 1.5 kilogram soccer ball is thrown vertically downwards on a hard surface with the same velocity as the stainless steel ball. After the collision with the surface, the soccer ball rebounds vertically upwards. Now what they're saying here is that we now take a different ball on the same surface here that we have. We throw it with the same velocity, right? The same velocity as this ball. But this ball, you have to understand that it's slightly deflated. So this means it's a bit soft. It's a bit elastic. It's not hard compared to the steel ball. Now, this ball will then eventually come here and collide with the surface. When it collides with the surface, it's definitely going to experience a force in the same way as the steel ball did, right? Let me do this. It's going to experience a force in the same way that it did. This force will be a time varying force, right? So it will be a force that is exerted over a certain amount of time here. Change in t. I'll say change in t of the ball. just to distinguish it away from this one. Now, you have to notice that this ball, because it is soft, it is deflated, it will be in contact with the surface longer than it is here. It will take a long time here, even though we're not told that time, but it will take a longer time to be in contact with the surface because it's soft. It will spend time, our varying forces, when the forces here emerge, they will take time to push back this object with this force here, the average of all those forces. It will take time to be in contact with the surface. Very important to observe that. And they say to us that this ball, after it experiences this force will be good enough to actually make the ball to go upwards. So the ball will then go upwards here with some velocity there. Now you have to note something. This ball will not reach this height here and it will not have this velocity because it's actually experiencing a smaller force compared to this situation here. We know that from the Newton's second law that the net force is inversely proportional to the time. So this means that this ball here, when it spends a long time with the surface, in contact with the surface, our force here has to be a small force because we have a big number here for the time. So our force will decrease and become a small force. But here you can see that we spend a very small time because this ball is hard. It's just going to hit the surface quickly and go up. So because we have a small force, a very short time here, we have a bigger force. In fact, that's why we got the force of 13,500. So this force here will reduce really in this case. Because now the surface is pushing this ball with a small force, it won't go to a bigger height in the same way that this ball did. This force is so small that the ball will reach a point below this height here. Will reach a point below this height here. I hope that makes sense. And you are able to see that. Now, I think we are done with interpreting the problem because remember I was interpreting the problem on the information that I was given. Now I can classify this problem. Obviously, I can see that it's a problem that uses Newton's second law. Already we were doing that when we were interpreting. And also it will require us to use impulse. Maybe they can ask us about impulse because remember, the force and impulse are directly proportional. So they might ask us what is the impulse here maybe, or anything along those lines. So I think that problem will fall under that. So that's classification. Now we are ready to answer our problem. The question says, how will the average force exerted on the ball, the soccer ball, by the surface compare? How will it compare to that exerted on the stainless steel ball? I think we actually answered this question really during our interpretation because they're saying how will this force exerted on the ball by the surface compare to this force exerted on the stainless steel ball by the surface. I mean, from Newton's second law, as we were explaining here, we can see that the force of the ball, of the soccer ball, would be smaller than the force exerted on the stainless steel ball. So they say to us, only write greater than, the same, or less than. So our force will be less than. We actually just interpreted that. So we are on question 1.3. 1.3, and our option is no, not greater than. We said our option would be less than. You can also answer this question using the change in momentum because remember, there is a relationship between the change in momentum and impulse is related to the force. So if you use the fact that the change in momentum is given by this formula, you can see that when we look at the first ball here, we will have the mass and velocity here, subtract the mass and velocity here at the beginning, which is negative 15, and you will get this value of 27 that we calculated there. But now if you look at this second ball here, the soccer ball, you would see that the velocity here will be smaller than this velocity because it doesn't get to this point. So it means here I'm going to have a small number. And then I'm subtracting from that small number another number there. So this makes the whole of this momentum, change in momentum, to be smaller. Right, so it means the momentum that I get of 27 here will be smaller, will be bigger than this one here. So this is to say here now that my change in momentum of the soccer ball is smaller than, so this is the soccer ball, is smaller than the change in momentum of the stainless steel ball. So the momentum of the soccer ball, right, will be smaller compared to the momentum of the stainless steel ball, because our velocity here is small. So when I subtract the momentum here to this momentum here, I'll get the smaller value compared to when I was doing the stainless steel ball. But momentum, change in momentum and impulse are exactly the same. They are equal from the impulse momentum theorem. We're saying these are equal. So it means automatically here that the impulse of the soccer ball will also be less than the impulse of the stainless steel ball, right? Because these two are equal. If I get this change in momentum is the same as the impulse, right? So if I'm saying the impulse of the soccer ball is small, if I'm saying the change in momentum of the soccer ball is small to the change in momentum of the steel ball, then that means automatically that even the impulse will be small because they're equal. Now, you also then have to realize that impulse is directly proportional to the net force. Impulse is directly proportional to the net force. So because I'm saying this side I have a small impulse, it means I must also have a small net force for the ball, right? And here I'm going to have a big net force for the stainless steel ball, right? So that's how we're going to say the force of the soccer ball is less than that of the stainless steel ball. So that's another way of doing it. It needs a bit of practice. That's why I didn't actually start with it. I think the first one is a much more simpler way of looking at this question. Let us run quickly through how they're going to mark this question. We have 2, 3, 3, and 1. We spoke about how you get the 2 marks in 1.1. In 1.2, the 3 marks will come from writing the formula, the substitution. Now this is the same as this. So if you write this, you get 1 mark. If you write this, you get 1 mark. It's the same thing. Then you'll also get a mark for writing the final answer and the direction. Then here you'll also get 1 mark for the formula and another mark for the correct substitution. Then you'll get the 3rd mark for writing the answer together with the direction. And the last question really is just 1 mark.